Okay, this is part of the FE handbook that talks about fluid flow, and in particular it talks about laminar flow in either circular tubes or between plates. So this is really one-dimensional flow. And what I wanted to point out is this equation right here. You might recognize this equation, but it's basically the equation of a parabola, where I'm just going to draw the axes here. This axis right here is, let's see, I get a different color. So this is the velocity. This is r. Let's call this 0. This is plus r and minus r. And at some distance that we call capital R, plus and minus capital R, we know that the velocity, when r equals capital R, we know the velocity goes to 0. So at those points on this graph, the velocity is 0, and otherwise, when r is 0, you can see when the little r is 0, that we have the maximum velocity. So this is V max, and the distribution is just basically a parabola, and I'm doing a terrible job of representing a parabola, but this is the locus of each of the velocity vectors as a function of r. So, yeah, again, this is supposed to be a parabola. It's supposed to be a parabola, and so what this tells you is that the velocity is parabolic inside this 1D flow, in between the pipe either or the plates. So the velocity profile is parabolic. And then they give you some guidelines here telling you what for turbulent flow, the value, circular tubes, etc. So there's some numbers here that you can use, and they also tell you that in this case, again, we're laminar flow, the shear stress has a distribution that is simply, I don't know if you can see this, tau over tau w, tau at the wall, that's what the tau w is r over capital R. So now this is a bit odd, but you recall that earlier in the FE content, it shows you that the shear stress is equal to what is that called? Viscosity times the change in volume, velocity volume with respect to, in this case, r, the y-axis. So if you took the derivative of velocity here, d with respect to r, in this equation, you would find out that this is basically equal to a constant times r. And so, in other words, it's the slope of this curve. Now, what's funny is in this case, the v, you kind of have to, you're taking the derivative of v with respect to r. So tau would be 0 here, and it would be a maximum value, of course, over here at the wall. So it's just the slope of this curve. The slope again being dv dr. So kind of rotating this whole thing. Normally we're used to saying dy dx, and this is kind of on its side. So all this equation is saying is that the maximum shear stress you'll get is at the wall, you'll get minimum at the center, and in between it's just proportional to the value of r over r.